Too many electric motors, and they should. Why? Well, usually it is because of inadequate maintenance. A good maintenance program is designed to prevent the development of motor problems and detect motor problems before they lead to a breakdown or cause expensive damage. So one part of maintenance involves routine tasks which help keep a motor running right. The other part involves inspections and tests to tell if a motor is not running right. Let's look first at typical routine maintenance operations intended to prevent problems from developing. There are three main areas of concern: lubricating bearings, keeping motors clean, and servicing the brushes and commutator on motors which have them. A maintenance schedule for these operations is a useful guide. It should tell you when to lubricate the bearings, for example, and what kind of lubricant to use. Do not lubricate more often than recommended, and do not over-lubricate. Too much oil or grease in a ball or roller bearing will actually increase friction and heat, and probably leak out. Preferably, the motor should be warm and running. Be sure no dirt gets in the bearing along with the oil or grease, and wipe up excess or spilled lubricant. Look and listen while you work. Remember that routine lubrication provides a good opportunity to detect problems that might be developing. For example, suppose you noticed that the motor got quieter when you greased the bearing. This might indicate a bearing problem that should be checked out. Feel the housing to see if it is hotter than it should be. Make a note to have the shaft checked for bearing looseness when the machine is not in operation. Cleaning the motor helps it run cooler and last longer. Dirt interferes with free airflow through open motors and around enclosed motors and insulates parts so they cannot dissipate heat. Dirt can also damage insulation and allow arcing and current leaks. Wipe dirt off all motors and vacuum the dirt out of open motors if possible. Do not use an air hose, since the air blast can force dirt and grit down between the winding turns, where it will be more likely to cause insulation damage. Many motors need periodic disassembly for more thorough cleaning and inspection. Even totally enclosed motors may need occasional cleaning out. Be sure power is locked out, and begin by removing the fan shroud on totally enclosed fan-cooled motors. Clean off the fan, the inside of the shroud, and the vents in it for free air flow. Replace the fan if it is damaged. Then inspect the connections in the junction box. Dried or burnt tape or insulation on a power line splice means not only that a short is likely to develop, but that the connection inside has higher resistance than it should. Remove the insulation and thoroughly clean the wire ends or terminals before reconnecting the wires. In a DC motor, conductive particles worn off the brushes or commutator can allow current to run over the outside of insulation, burning it and interfering with proper motor operation. Some kinds of insulation material can be damaged by oil, which may have leaked out of the bearings. Check for bad bearing seals. The oil may have been left by oily air pulled through an open motor. In either case, careful cleaning is essential, but do not use solvents, which could also damage insulation materials. Localized burnt areas on the winding insulation or taping probably mean a short of some kind. The winding should be checked further before the motor is put back into service. If a motor has a centrifugal switch, check the parts for wear and the contacts for excessive burning or pitting. Fresh grooves or shiny spots on the rotor and stator probably indicate rubbing due to a bent shaft or loose bearings. Clean out the motor thoroughly before you put it back together. And as you reassemble it, check for loose bearings or a rough feel in the bearings. Finally, routine maintenance includes servicing the brushes and commutator in DC motors and some AC motors. In most motors, you can see the brush commutator contact if you remove an inspection or access plate. Check for sparking when the motor is running under load. Shade the light if necessary. Slight sparking is okay in some motors which run intermittently or under light load, but any sparking in a motor under heavy use means that internal damage is being done. Practically anything that interferes with good electrical contact will make the brushes spark. The commutator must be smooth. If the motor has been running normally and under load, it will have a brown glaze. Grooves or ridges, burning or pitting of the bars, or high mica between the bars all require motor disassembly and repair. The brush rigging, including the brush holders and the springs which press the brushes against the commutator, must be in good shape. The brush holder should be squarely aligned so that the long dimension of the brush is exactly parallel to the commutator bar. Any looseness or misalignment of the brush holder around the commutator will cause problems. Even if the brushes appear to be operating properly, check brush length and condition. Often you have to remove them to check their length. As a general rule, all brushes in a motor should be at least half as long as a new brush. If no brush in the motor is worn down enough to need replacing, be sure to put each brush back exactly as it was in the same brush holder and not turned end for end. They have worn into the shape of the commutator and may not contact the commutator as well in another position. Be careful not to chip or break the brushes. They are deliberately made of a relatively soft carbon, so they will wear before the copper commutator bars do. As a result, brushes are rather fragile and must be handled carefully. Now, if one or more brush is down to half its original length, worn crooked, chipped, or broken, it is a good idea to replace the complete set. Use brushes of the right hardness grade for the motor. Be sure the new brushes go in so that the bevel on the end, if there is one, matches the commutator, and that the brushes fit properly in their holders. They should be free to slide in and out, but must also be held snugly so they cannot chatter or wear crooked. Check the specifications to make sure the brush holder is the right distance from the commutator. Adjustment may be necessary if the commutator has been turned down or if the brush holders have been moved for any reason. Also, be sure the flexible brush leads are not grounding out anywhere and that any insulation on them is in good condition. Check especially carefully the brush holder that any short brush came from to be sure it is not loose, crooked, or out of position. Brushes usually need to be seated. In other words, they must be shaped to match the curve of the commutator exactly. The best way to do this is with a strip of fine sandpaper around the commutator. Make sure the sandpaper follows the curve of the commutator and does not round off the end of the brush. Do not use emery paper or emery cloth. The abrasive particles are conductive and could wedge in the motor, causing shorts. A brush seating stone is also available. It is held against the commutator as the motor runs and will both polish the commutator and wear off the end of the brush slightly for a better fit on the commutator. Stones for resurfacing the commutator are also available. They must be used carefully, and you've got to know what you're doing. DC motors are expensive and easily damaged. Finally, after you've installed new brushes, check them for sparking when the motor is running to make sure you've installed them correctly. Now, the other part of motor maintenance involves inspection and test on motors to detect problems before they become obvious or lead to a breakdown. Some of the tests are as simple as watching and listening to the motor. If a centrifugal switch flashes abnormally, something is wrong. The motor may still run all right, but the switch will probably fail soon. If an AC motor hums or buzzes, it may be under too heavy a load, or it might also have loose core laminations. Vibration, squealing, or dragging or scraping noises in any motor probably means serious bearing problems or a rubbing rotor. Other motor problems may not be so obvious, however. To find them before they damage the motor takes instruments and careful record keeping. In many plants, for example, the insulation inside a motor is periodically checked with a megometer. Unlike a standard ohmmeter, which uses a small battery to push current through the test resistance, a megometer uses a high voltage equal to or greater than normal power line voltage. This allows it to measure very high resistances accurately. It also puts the insulation under high voltage stress, so defects are more likely to show up. Using a megometer is different from taking a reading with a standard ohmmeter. For one thing, remember the voltage involved. Do not touch the lead clips or probes while applying megometer test voltage, and make sure the voltage will not be applied to any solid-state equipment connected to the motor lines. If there is any question, disconnect the motor lines before applying the megometer test voltage. Second, you may need to interpret the reading. Usually, a good motor will quickly produce a very high reading of at least several hundred megohms or even infinity. A much lower reading, however, does not necessarily mean a motor problem. High temperatures and humidities will reduce the reading significantly. Also, the insulation in some motors needs time to charge up, like a capacitor. Some test procedures specify keeping the voltage applied for as much as 10 minutes. If the reading keeps rising and is at least twice as high at 10 minutes as it was at 1 minute, the insulation is probably okay. If the reading levels off quickly at a fairly low level, however, it is a sign that leakage current is flowing through or over the insulation. This current will probably cause further insulation breakdown until shorts develop and the motor fails. Megometer readings are most useful when they are taken regularly over the life of a motor. Ideally, they should be taken under the same temperature and humidity conditions or corrected for temperature and humidity. The readings will normally decrease slowly as the motor ages. If a new reading is much lower than the last reading taken a few months before, the motor should be watched carefully in the weeks or months ahead. If the readings continue to drop rapidly, plan to replace the motor. Taking a megometer reading charges the insulation like a capacitor. It should be allowed to discharge. If your meter does not have a discharge feature, carefully short together the points where you had the probes attached. Complete discharge may take some time. The general rule is to leave the short in place at least 4 times as long as the voltage was applied by the megometer. Sometimes the problem indicated by a megometer is not bad insulation, but moisture or dirt. Drying out a damp motor will raise the measured resistance considerably. Checking a motor's frame temperature is also important. Whatever kind of instrument you are using, be sure to measure the temperature after the motor has been doing its normal job for some time, and always take your readings under the same conditions so you can compare them and spot a motor that is starting to run hotter than usual. If you find a temperature reading that is significantly higher than past readings on the same motor, it means something is wrong, and you should determine what it is. In many cases, other symptoms will help you find the problem. The motor or the equipment that it is driving may be vibrating, making unusual noises, or operating slowly as if loaded down. Belts may be hot or smoking, or the motor may be cycling on and off too frequently. Other checks include measuring the voltage at the operating motor. If the voltage on one or more phases is lower than normal for any reason, the motor will overheat. Induction motors are particularly sensitive to low voltage and will sometimes stall completely if the voltage drops as little as 20%. Current readings are also useful. If the current in all lines to the motor is high, the motor is overloaded. If the current in only one of the power lines is high, with normal voltages, suspect an electrical problem in the motor. Resistance readings will sometimes pinpoint electrical problems in the motor. Lock the motor out first. Disconnect the power lines. Occasionally, a 3-phase motor will also have a neutral as well as power line connections. Disconnect it too. Then check resistance between the motor frame and the motor leads. use the highest ohm scale. On most simple ohmmeters, anything but an infinite reading is a sign of some kind of short to ground. The capacitor on capacitor start motors should also be checked periodically. Use the motor's wiring diagram to locate the appropriate terminals. Short the terminals together to be sure the capacitor is discharged. Then, measure the resistance across the terminals. The initial reading may be quite low, but it should build up quickly on a low resistance scale, slowly on a high resistance scale, nearly to infinite as the ohmmeter battery charges up the capacitor. If you find steady low resistance, the capacitor is shorted. An immediately infinite reading means that something in the circuit is open. Defective capacitors are easy to replace. Be sure the replacement is the same capacity in microfarads as the original and has a voltage rating at least as high. The capacitor must be able to stand a much higher voltage than the motor supply voltage. All these tests and the routine procedures and inspections we've outlined are intended to prevent motor failure. Maintenance is much easier than troubleshooting and repair, so it is always worth taking the time to do maintenance procedures properly and to look closely for signs of problems. Periodic inspections and test readings to spot potential problems allow you to anticipate motor failure and avoid an unexpected breakdown.